CEDAR virtual meeting participants. This is Aptam from Ethiopia, Bahir Dar. I'm gonna present you my work entitled by a method of estimating equatorial plasma vertical drift velocity and its performance using NOFs observations. Actually, this work was presented as a poster presentation in ICE 2019, Trieste, Italy. Let me move to the outline, and there will be some background of the study discussion, modeling techniques, results, and finally concluding points. Background of the study. The ionosphere of the Earth exhibits many interesting and unique plasma processes. There is an interesting dynamo in the upper atmosphere of the Earth. Among that, the dynamo, the neutral dynamo, the neutral atmosphere motion produces electric field horizontally and vertically, and those produced electric fields interact with the geomagnetic field and produces motion of ions. Especially on the equatorial region, the Earth's magnetic field is much of horizontally oriented, and the interaction of this horizontally oriented magnetic field with the electric fields produces vertical motion of ions and zonal motions of ions depending on the orientation of the electric field produced. It may be the electric field may be zonal or horizontal or vertical. So this is the dynamo, figuratively E and F region dynamo. We can see also the ionization crust here. We can see the orientation of the magnetic field, the geomagnetic field. South pole over here and north pole. So the field, as you can see, is oriented in this way, and it is horizontal over the equatorial region. And the electric field produced due to the E region dynamo maps through these equipotential field lines and interact with the magnetic field and produces what we call the ion drift, vertical drift or zonal drift. It depends on the electric field produced. The drift is responsible for equatorial ionization anomaly EIA and creates conducive condition for equatorial spread ESF by driving the plasma to higher altitude, particularly during the evening time. These disturbances EIA and ESF are known in disrupting the trans-ionosphere, propagating radio wave dependent technologies or communications, so that models are developed to predict what will happen in the future. And as you can see, these two guys produced a model in this year. Again, Anderson produced a model of vertical drift, and these two guys, again, this have been developed. What we found is models have been developed without or with very few ground observations from the African and Asian region especially, and these models have not been tested sufficiently in different longitudinal regions. Okay, modeling techniques. The new technique used parameterized and data-driven physics-based model. The data is obtained from ground magnetometers over different longitudinal sectors, over the South American sector, West Africa, and Asian sectors are used. Measuring the perturbation in the horizontal component of the geomagnetic field can provide a direct measure of EEG, equatorial electrojet current. The basic consideration is solar point current has the same effect both on the equatorial region, deep equator region, and off equator region, like 6 degree to 9 degree on both north and south regions. Okay, considering the EEG as a set of parallel wires, we can estimate the induced magnetic field from the EEG by using Ampere's law, equation 1, and by considering the EEG current as a current sheet, we can minimize Kx, G naught B with Kx, the dimension of ampere per meter. Then the EEG magnetic field measurement model can be represented by equation 2, where half is replaced by 3 or 4 for spherical symmetry of the Earth. The EEG current density and the east-west direct electric field can be related by equation 3, and this helps us to find out the electric field from this current density Kx. The electric field is therefore can be obtained by using Coulomb conductivity and height integrated Coulomb conductivity and the current density Kx. This produces the plasma drift at an altitude h in the F region due to mapping, since the electric field can map through the equipotential field lines. Therefore, we can have equation 4, which is our final model, a physics-based parameterized drift velocity model, or simply parameterized drift velocity model in our case, to estimate drift velocity using magnetometer observations. These are results, a sample of results actually. On the first column, this column is the EEG current density in nanotesla, and here is current density, sheet current density, ampere per meter, and this column is the electric field, where the blue one is the Fager and Scherlitz model, and the green one is ours prediction from Ohm's law, and the fourth one is the vertical drift. The final, our goal is to find out this one, the vertical drift. So we have evaluated with other models, Scherlitz and Fager model, Anderson model, the broken green line. The bold green line is our model, and the red dots are the observations from scene of satellite. So when you evaluate, you can see it, a good performance is obtained by our model and Anderson. Same thing over here, the same thing here. So it's a good performance. The same is obtained over here. Actually, on this one, on figure 2, it is over the Peruvian sector, South America, and figure 3 is over West Africa, and figure 4 over the East Africa, and finally the East Asia, Thailand. So a good performance is obtained for our model. Finally, we can conclude that in this work, two well-known drift velocity models are validated against a new technique of estimating vertical plasma drift velocity using parameterized and data-driven physics-based model. Mostly the PDV model agreed well with the NOFs measurements, except on few hours of sun days compared to other models. Mostly, sorry for the repetition here, it's the same concept. Thank you so much. This is my address. Thanks so much again. And this is Haptamu. Thank you again. Thank you so much.